All right, get ready to dive deep, deep into the fabric of reality itself. We're talking about Roger Penrose's The Road to Reality today.
Oh yeah, a classic.
And look, we're not going to try to cover the whole book, right? This is more like a treasure hunt, pulling out the most mind-blowing bits about how math shapes everything around us.
From basic shapes to those quantum mysteries that make your head spin.
Exactly. And this one's for you if you love big ideas. A&D want to walk away with some real aha moments to ponder. Like, imagine trying to explain to someone that those Escher drawings, the ones with the fish that seem to get smaller and smaller?
Yeah, the tessellations.
Those are actually a way to visualize hyperbolic geometry.
Where the shrinking is more about how we see it through our Euclidean lens than actual changes in size.
Whoa, right. But hold on, it gets even crazier. Did you know that those so-called imaginary numbers, the ones with the square root of -1, those are actually fundamental to the laws of physics at the tiniest scales? I mean, come on. And then Penrose throws in this thing called the Dirac equation, which somehow manages to combine quantum mechanics and special relativity.
Using these bizarre, non-commuting quantities.
It's like finding a secret passage between two totally different worlds. Now, I know all this might sound super complex.
Yeah, you might be thinking, what does it all mean for me?
That's where you come in, our expert guide through these mind-blowing theories.
I'll do my best to break it down.
Awesome. Okay, let's start with something I think we all remember from school, the Pythagorean theorem, a squared plus b squared equals c squared.
Good old Pythagoras.
Seems pretty basic, right?
At first glance, sure. And Penrose illustrates it beautifully in the book using similar triangles, figure 2.9, I think. But here's where things get interesting. What if I told you that the Pythagorean theorem isn't always true?
Hold on, what? How is that possible? It's a theorem.
It's a theorem, yes, but within the world of Euclidean geometry, the flat space we normally think about. But there's this whole other type of geometry called hyperbolic geometry.
Oh, right, like those Escher fish?
Think of it like this. In hyperbolic space, parallel lines can actually move apart, and triangles have angles that add up to less than 180 degrees. It's a whole different ballgame.
So you're telling me in this warped space, the Pythagorean theorem doesn't work. What does that even mean for our universe?
It means the universe might not be that flat Euclidean space we imagine. It could be curved, shaped in ways that break our everyday intuition. And Penrose is hinting at a connection between these abstract geometry ideas and the structure of the cosmos itself.
Mind-blowing. So geometry is way more complex than we thought. But surely something like real numbers, the numbers we use every day, those are solid, right?
Well, even real numbers are more of a mathematical invention than we realize.
Wait, what? How can the numbers we use to measure everything not be real?
Good question. Penrose gets into something called a Dedekind cut, which basically defines real numbers using sets of rational numbers.
Okay, lost me a bit.
The takeaway is that our measurements of things like length and time, which we write down using those real numbers, don't perfectly match the infinite precision that real numbers theoretically have.
So there's like a disconnect between the math and the physical world, even when we're just measuring something.
It suggests there might be deeper levels of reality where that mismatch actually matters, where things are more granular than real numbers can handle.
Okay, my brain is starting to hurt. Before we fall too far down that rabbit hole, let's talk about complex numbers. Penrose claims that the laws governing the smallest stuff in the universe are based on these complex numbers. We just started accepting that real numbers might not be so real, and now we're dealing with imaginary ones. This is getting intense.
Hang on tight, this is where it gets really magical.
Okay, I'm intrigued. What makes complex numbers so special, especially when we're talking about physics?
Well, think about Euler's formula. E to the power of I times pi. Plus 1 equals 0.
Yeah, I vaguely remember that from somewhere.
It connects some of the most fundamental constants in math, all in one beautiful equation.
I have to admit, that's pretty impressive.
It gives us a peek into the deep connections between different mathematical ideas. And then there's the Mandelbrot set. It's this infinitely complex fractal that comes from a surprisingly simple equation involving complex numbers.
Fractals, those are the trippy, infinitely repeating patterns, right?
Exactly. It visually captures the crazy complexity that can emerge from simple mathematical rules.
Okay, I'm starting to see the magic here. But how do these complex numbers actually work in the laws of physics? How do they control how particles behave?
So remember we talked about the clash between quantum theory and relativity. There's this concept called energy positivity that's important in relativistic quantum mechanics. And the usual way we calculate energy doesn't quite fit within the relativistic world.
Like trying to cram a square peg in a round hole.
Exactly. And that's where Dirac's genius comes in. He figured out how to basically take the square root of the wave operator, which describes how waves move in quantum mechanics.
Taking the square root of an operator, what does that even mean?
It's a bit complicated. He used something called Clifford algebra to do it. But here's the kicker. This trick not only satisfies the rules of relativity, but it also gives rise to the electron's spin.
So by solving a math problem, he actually discovered one of the most fundamental properties of particles. That's wild.
It shows the deep connection between abstract math and the inner workings of the universe.
Wow, I'm starting to get a glimpse of how profound that connection really is.
And it gets even weirder. Penrose talks about this zigzag picture of the electron, which shows how they're constantly creating and destroying virtual particles.
Virtual particles, those are particles that don't actually exist, right?
Not in the way we normally think about it. They're more like fluctuations in the quantum fields that are everywhere.
Okay, still trying to grasp that one. But how does this relate to the standard model of particle physics?
That zigzag picture is actually showing how particles interact according to the standard model. These virtual particles act like carriers of forces.
Like the photon for electromagnetism.
Exactly. It's through these virtual particles that all the particles talk to each other.
So there's this whole hidden world of virtual particles orchestrating everything. Amazing.
And the standard model describes all the known fundamental particles and forces except gravity. But even though it's incredibly successful, Penrose does mention some of its limitations and explores alternative ideas, like the Chun-Tzu model.
So even with all our advancements, there's still so much we don't know.
Oh yeah, there's always more to discover.
That's what makes this so fascinating. I'm ready to dig even deeper into these mysteries. Stick with us as we continue this wild ride in the next part. And we're back for more deep diving into the fabric of reality. Last time, things got pretty wild. We saw how even basic ideas like geometry and numbers can get incredibly complex when you really dig in.
Right, and then we jumped headfirst into quantum mechanics with those mysterious but beautiful complex numbers.
Totally. But before we go any further down that quantum rabbit hole, I keep thinking about this one line from the book. Penrose writes, "It appears to be a universal feature of the mathematics. You know, the math we think underlies how our universe works, that it fundamentally depends on the infinite."
Yeah, that's a big one.
What do you make of that statement? How does infinity shape how we understand the universe?
That's a great question. And it gets at one of the biggest mysteries in both math and physics, the whole idea of infinity. It seems like wherever we look in the universe, from the tiniest particles to those massive structures, we run into this concept of the infinite.
It's a pretty profound thought, right? Can you give me some concrete examples of how infinity shows up in our models of the universe?
Sure. Think about those real numbers we talked about. They extend infinitely in both directions, towards the infinitely big and the infinitely small. Then there's the question of space and time themselves. Are they truly infinite? Do they go on forever? We don't really know.
And what about the quantum world? That realm seems full of infinite possibilities, maybe even parallel universes. Does infinity play a role there too?
Absolutely. Quantum mechanics is full of infinities, and physicists are still trying to figure out how to make sense of them all. But it's not just about size. It's also about the precision of our measurements. Theoretically, we could keep measuring things to an infinitely accurate degree, but in reality, it seems like the laws of physics themselves set a limit.
Wow. So even measurement, a fundamental part of science, is tied to this concept of infinity. How does that affect our ability to understand the universe?
Well, it suggests there might be a fundamental limit to what we can understand, a limit set by the very nature of infinity. Penrose even suggests that maybe the math tools we have now aren't powerful enough to fully grasp the infinite. He hints that there might be new, more powerful mathematical frameworks out there waiting to be discovered, frameworks that could bridge the gap between the finite and the infinite.
That's both exciting and a little bit intimidating. It's like we're standing at the edge of a huge, uncharted territory. But I'm ready to explore. Let's bring it back down to specifics for a moment and revisit that Dirac equation. You explained how it brings together quantum mechanics and special relativity, but I'm still a bit fuzzy on how it actually works. Can you break it down for me again, focusing on those key elements that make it so revolutionary?
Absolutely. So remember, we're dealing with this inherent tension between quantum theory and special relativity. Quantum theory says particles can exist in multiple states at once, this concept called superposition.
Right, like they can be in two places at once.
Exactly. But special relativity complicates things because it says nothing, not even information, can travel faster than light.
Right, and those two ideas seem like they clash. How do you even begin to reconcile them?
That was the problem Dirac was grappling with. He knew the standard Schrödinger equation, which describes how quantum systems evolve, just wouldn't work within the framework of special relativity.
So how did he crack this puzzle? What was his big breakthrough?
It was truly ingenious. Remember we talked about the wave operator? It basically describes how waves move in quantum mechanics. Dirac realized that he needed to find a way to, in essence, take the square root of this wave operator.
Okay, hold on. Taking the square root of an operator, that sounds incredibly abstract to me.
It is. He used something called Clifford algebra to do it. But here's the amazing part. Not only did this mathematical trick satisfy the demands of special relativity, it also, kind of magically, gave rise to the electron spin.
Whoa, wait. So by solving a math problem, he stumbled upon one of the most fundamental properties of particles. That's mind-blowing.
It is. It shows this incredible connection between abstract mathematical insights and those profound physical discoveries. It's like he opened a secret door between two seemingly separate worlds.
Feels like we're starting to unlock deeper levels of reality with every new concept we explore.
And it gets even weirder. Remember that zigzag picture of the electron we mentioned before?
You mean the one that shows virtual particles constantly popping in and out of existence?
Exactly. That picture helps visualize how the Dirac equation describes electrons as constantly creating and destroying these virtual particles.
So beneath what we see as reality, there's this whole hidden world of quantum fluctuations going on.
Precisely. And these virtual particles are crucial. They act like the carriers of forces, like the photon being responsible for electromagnetic interactions. It's through these virtual particles that all particles interact with each other.
So this seemingly abstract math equation, the Dirac equation, is actually describing this unseen world of particles and forces that shape the reality we experience. That's incredible. What are the implications of that?
It suggests that the reality we see is just the tip of the iceberg. There's this deeper level governed by quantum mechanics and described by this beautiful and complex math that underpins everything we see and experience.
It's both awe-inspiring and a bit humbling, isn't it? It makes you realize how much more there is to discover about the universe. But before we dive even further down that quantum rabbit hole, you mentioned that the Standard Model, which builds on the Dirac equation and these other quantum field theories, it has some limitations. What are those limitations, and what do they mean for our understanding?
So the Standard Model is incredibly successful at describing the fundamental particles and forces we know about, but it doesn't include gravity. And there are some other mysteries it can't explain, like why do we have 3 generations of particles, each with the same basic properties but different masses? And what about dark matter and dark energy, which seem to make up most of the universe but don't fit into the Standard Model?
So despite all its success, the Standard Model is still incomplete. Where do we go from here?
Exactly. And Penrose, always pushing the boundaries, explores those limitations and looks at some alternative ideas. He mentions the Chance model, which tries to address some of the Standard Model's shortcomings.
Sounds like the search for a more complete understanding of the universe never really ends.
Never. It's an exciting time to be watching these developments. String theory, twister theory, loop quantum gravity, all these approaches are pushing our knowledge and opening up new ways of understanding the universe. Who knows what breakthroughs are waiting for us?
That's the beauty of it, right? There's always more to learn and explore, but I think we need a moment to let all this information sink in.
A little breather is a good idea. We'll pick up this conversation in the final part of our deep dive and explore even more radical ideas about the fabric of reality.
And we're back, ready to wrap up our deep dive into the fabric of reality. We've journeyed through some truly mind-bending territory, from the complexities of geometry and numbers to the quantum world.
And last time, we even touched on some of the big mysteries that still puzzle physicists today.
Right. Even with all the success of the Standard Model, there's still so much we don't know. Are you ready to explore some of those even more radical ideas that might hold the keys to unlocking those mysteries?
Absolutely.
Yeah.
Penrose certainly doesn't shy away from the big questions.
That's what I love about him. So as we were discussing, the Standard Model has its limitations. It's like we have this incredible puzzle, but we're missing a few crucial pieces.
Exactly. And one of the biggest missing pieces is a theory that can unite quantum mechanics and general relativity, what physicists call a theory of quantum gravity. It's like the holy grail of modern physics.
The quest for a theory of everything. So where do we even begin to look for it? What are some of the most promising approaches out there?
Well, there are several avenues being explored, and Penrose walks us through some of them in the book. One that gets a lot of attention is string theory. We touched on it briefly before.
Yeah, where the fundamental building blocks of the universe are particles, but these tiny vibrating strings.
Right. And one of the interesting, some might say controversial things about string theory is that it requires extra dimensions beyond the three spatial dimensions we experience.
Whoa, extra dimensions. That's pretty mind-blowing.
It is. To make the math work, string theory suggests there are 10 or 11 dimensions curled up and hidden from us. It's a mathematically beautiful theory, and it has the potential to bring together all the fundamental forces, including gravity, which has been the biggest challenge.
I'm trying to wrap my head around that. But if string theory has so much potential, why are some physicists, including Penrose, still a bit skeptical?
Well, Penrose is a very rigorous thinker, and he raises some important questions. For example, one of the main criticisms is that string theory hasn't yet made any clear predictions that can be tested experimentally.
Ah, so it's hard to prove or disprove.
Exactly. It also relies on incredibly complex mathematics, which makes it challenging to grasp fully.
So it's a promising avenue, but it still has some hurdles to clear. What are some of the alternatives to string theory?
Penrose himself is a big advocate for twistor theory, a mathematical framework he developed.
Oh, right. I remember reading about that. It's a totally different way of looking at reality, right?
Yes. It suggests that the fundamental building blocks aren't points in space-time, but these things called twistors.
Hold on, twistors. What are those exactly?
Think of them more like rays of light.
Wait, rays of light as the building blocks of reality.
I know, it sounds strange, but twistors have these unique mathematical properties that make them really suitable for describing space-time, especially within the framework of general relativity.
So it's like a whole new lens for viewing the universe.
Exactly. And by using that lens, we might see things we couldn't see before.
I love that analogy. Does twistor theory offer solutions to those problems that string theory struggles with, like unifying gravity with the other forces?
It's still being developed, but it's showing some real promise, especially in areas where string theory has run into trouble. For example, twistor theory has been used to make interesting calculations about particle interactions in quantum field theory.
So it could potentially shed light on the nature of quantum gravity.
It might. It's a fascinating area of research.
It seems like this quest to find a unified theory of everything is far from over.
Definitely not. And that's what makes it so exciting. Both string theory and twistor theory, along with other approaches like loop quantum gravity, are pushing the boundaries of physics. Who knows what amazing discoveries lie ahead?
Absolutely. Now, before we wrap up this incredible journey, I wanted to touch on one last thought from Penrose. He ends the book with this beautiful statement. We are all a part of the vastness of the universe, and yet the universe is also within each one of us.
Ah, yes, a powerful statement.
What do you think he meant by that?
It speaks to the profound interconnectedness of everything. We're all made of stardust, literally formed in the hearts of stars. And those same physical laws that govern the stars and galaxies also govern us. But at the same time, we're conscious beings, able to experience the universe in our own unique way.
So we're both tiny specks in this vast cosmos and the essential participants in the story of the universe.
Exactly. It's an incredible duality that makes exploring reality so fascinating and rewarding. We're part of something much greater than ourselves, and yet that something greater is also a part of us.
That's a truly inspiring thought to end on. Well, I think that brings us to the end of our deep dive into the fabric of reality. It's been an amazing adventure exploring these mind-blowing concepts.
I've thoroughly enjoyed it.
And for everyone listening, if you're ready for more, I highly recommend checking out The Road to Reality by Roger Penrose. It's a challenging but incredibly rewarding read for anyone curious about the profound connection between math and the universe. Until next time, keep questioning, keep exploring, and keep looking up at the stars, knowing that you carry a piece of that vast universe within you.
Thank you for tuning in to the Power Book of Podcasts. If you enjoyed this episode, don't forget to hit the subscribe button and join our growing community. Click the bell icon so you never miss an update. We have so much more inspiring content coming your way.